Hello, everyone. Today we're going to talk about the future of energy efficiency, case studies and solutions that work, presented by Sustainable Project Group and Agro Resilience Kit, or ARC. Agenda of today will be an introduction about ourselves and our companies. We will go a little bit in the depth of the current situation, and then we will talk about passive radiant heating and cooling systems. And during the presentations, feel free to ask some questions, or after the presentation, we will answer them as well. Presenters of today will be myself, Robin Lucidarm, Business Development Manager, and Dan Cloutier, President of ARC.
Go. So with ARC and my various work in building efficiency and cogeneration, solar technologies, that kind of stuff, I've been involved in these areas since the early 2000s. And we partnered in a strategic alliance with Sprung Structures 9 years ago. Sprung's a very old Canadian business, which was founded in 1887. And what they provide is what's called tension membrane buildings, which is their head office and shows an excellent example of that kind of a unique building technology that they patented about 40 years ago and have been installing around the world ever since. And extremely energy efficient for a number of reasons that we'll touch upon, and can create additional energy efficiency layers, ultimately that make a great deal of business sense, either by saving money, and we typically focus on approaches that will result in a roughly 5-year payback, which by definition is about a 20% return on investment. And also we end up achieving those 5-year paybacks, if not by savings, but by opportunities to increase revenues. And we'll show you a few examples of those sorts of things that various commercial building operators, et cetera, have gone into. What we end up seeing when we look at this chart or these efficiency initiatives that Robin introduced you to is, of course, we've been after these things for quite a while as an industry. And so a lot of the low-hanging fruit, whether it's solar panels, whether it's installing high frequency or variable frequency drives, I'm going to say heat recovery, these sorts of things, most of the low-hanging fruit, or a lot of the low-hanging fruit, has been covered off. We like cogeneration a lot. There's lots of opportunity left there. Typically has an under 5-year payback. We like geothermal a lot. That typically, depending on the price of electricity, if you're heating with electricity, or the price of natural gas, that typically has about a 14-year payback. So it's sometimes more challenging to undertake for those reasons. So what we're highlighting here is one case study, which is very much a best practice. So what's encompassed in this chart is, from a few years ago, the very most efficient buildings in Canada. And then what Natural Resource Canada did with their extensive database of Canadian buildings is they looked at these buildings and said, if they had not adopted the technologies and approaches for energy efficiency that they did, would they have performed down here, as opposed to against the Natural Resource Canada database that shows what their performance would look like. And so mostly we see excellent improvements, and the building we're going to focus on is Manitoba Hydro's head office, called Manitoba Hydro Place, not very far from the corner of Portage and Main in Winnipeg. And so what Natural Resource Canada's database shows is that that building would typically use about 375 kilowatts per square meter per year of energy. That's including all the thermal energy requirement and electrical energy and putting it in a kilowatt measurement. But because of the incredible technologies that Manitoba Hydro adopted, and the building's been open since 2009, what we see is they're slightly below 100 kilowatt hour per square meter annually. So you end up seeing, almost a 70% roughly reduction in energy consumption. And so really good savings. And we'll dive in a little bit into the how. So they did achieve a LEED Platinum level, which is incredible. They have 100% fresh year round because of their approach. It's very heavily focused on radiant heating and cooling. And about 50% of that radiant heating and cooling comes from the 280 boreholes that they drilled beneath the building. High capital cost for that. Not having any electricity or natural gas usage outside of the geothermal pumps operating is very impressive. Even more impressive, in our humble opinion, is what they call their solar chimney, which uses almost no electricity at all, just enough electricity for fans, which are basically, depending on the time of year, moving energy either this way for heating or that way for cooling, if you saw my cursor. And so really, really impressive technology that has been used all too little in North America, but is very heavily used in other parts of the world. In fact, the leading proponent of these designs and approach is actually Foster and Partners, which is the world's largest architecture firm. And the engineers that did the Manitoba Hydro project very often do projects with Foster and Partners. It took a while, a number of years, for Manitoba Hydro to become fully comfortable with the design. But all of these achievements have been monitored and publicized since 2009, as I say, when the building opened. So I don't know of another building that's 22 stories anywhere in Canada, let alone in such a cold environment, that really only uses a small amount of electricity, as you saw, and has no need for natural gas for space heating, thanks to the geothermal and this solar chimney, which is effectively a greenhouse on the south side of the building. So we've done some comparisons with that, and are pointing out here the huge value of passive heating and cooling, because here's Manitoba Hydro Place, and here's our demonstration greenhouse in southern Alberta, which is an R1 structure. So it's not the insulation that's doing most of the heavy work in heating and cooling the greenhouse. It's very much other things that we'll mention, such as air tightness, leveraging the sun in a very different way than we tend to. Although it is ways that is increasingly being promoted in Canada. So this is a graphic that came from Toronto City Hall, where they were looking at and promoting buildings doing exterior retrofits or exoskeletons, as they called it, quite similar to what Manitoba Hydro did. Those exoskeleton renovations can be extremely costly when we're looking at steel and glass and needing more footprint if it's available and these sorts of things. What we loved about the sprung structure solution that we promote is that it's made of very light membrane, a PVC membrane specifically, and aluminum. So the building is very light, in fact, such that you can create these exoskeletons. We'll show you a couple of examples, and it's feasible to do that by cantilevering off the building. So you can potentially permitting allowing do that right over sidewalks and that sort of thing. And it is the sort of thing that Foster and Partners does in a number of geographies, and so it does hold up as a best practice. By using tension membrane buildings, we're tensioning that PVC between two aluminum beams. And so we naturally end up with an unparalleled air tightness of about 2% air exchange. Just serendipitously ideal, such that you don't have sick building syndrome issues. You don't have costs to have a lot of air exchange systems and monitoring, but you end up with really, really great energy efficiency numbers. And then our unique clear membrane that we'll show you allows you to have an unparalleled capture of sun, solar heat or energy.
Dan, there's a question from the audience,
Please.
which is a good thing to explain. So Angie asked, can you comment on the tenant comfort at the Manitoba Hydro? Are the temperatures constant, and are there any hot spots or cold spots when you talk about this structure?
It's a great question. There has been challenges in some buildings with the controlling those temperatures tightly and having tenant comfort. And of course, when you don't have comfort, you end up with considerable challenges as a building operator. I believe that's been measured with Manitoba Hydro. I think that they've found minimal issues with that. And so I believe you can find that information on their website in various reports. It's not something that I focused in on too much depth, just trying to keep the brevity of this presentation. So thanks for that question. So as I say, air tightness is really a big difference maker. It's a best practice. And so we use the Yeti example here. When I first was introduced to Yeti, like a lot of people, I'm sure you've been amazed at how long your drink will stay cold or hot and so forth. And I thought initially that, gee, it must be some space age insulation of some type or what have you. In fact, when you go onto Yeti's website, what you'll find is they say the number one technology that gives them that ability is the air tightness of their product. They don't say exactly what that air tightness is. It might slightly or somewhat exceed a 2% air exchange, but most buildings in the world would be 4% is considered really expensive and hard to get to. 9% is really common. And in old buildings, there was no way anybody was below 9 and often higher. Greenhouse operators will tell you that anything from a 4% up air exchange, meaning small holes or ability for wind to unduly influence, just a 15 mile per hour wind in those uh, uh, conditions, low air tightness, that will actually double your heating and cooling cost. And so, yeah, best practice is air tightness, and Yeti understands that. So these are a couple of images from Manitoba Hydro, and what they're showing is this normally would be the outside of their building, typical kinds of construction. So you can call it an exoskeleton because this is what they call the solar chimney, and it's essentially on the greenhouse on the outside of the building. So when you want heating, the sun lets in, the glass lets in the sun. This space heats up as much as possible. This wasn't intended to be a space that people would occupy so much as be a utility cost-saving corridor. And so they have these openings where the hot air would rise through, and then fans would send that hot air through the plenums below the floors, which it interacts with their hydronic heating system from the geothermal field. And then it reverses when you want to cool. So then the cool air on the north side of the building is being driven through. But interestingly enough, the hot air is allowed to rise up. And that's where they call it the chimney. It's the chimney effect. It's literally pulling, as a chimney always does, the hot air up and pulling the cool air through the building so that essentially they have very low cooling requirement, and it can be supplemented with the geothermal cooling as required. So best practices put in place, well executed. It's interesting for us to note just how long some of these best practices have been in place. So that approach to cooling has been used in Iraq, Iran, formerly Mesopotamia, for about 800 years. And you can see buildings that use that even in Atlanta, in the US, and that kind of thing. Some technologies we got away from. In Greek times, they actually did the same thing by literally building their housing and other buildings so that the north of the building was just like this Frank Lloyd Wright building is built into the ground. Sometimes this is called earthship kinds of construction. And the south side is meant to have maximum exposure of windows and so forth, so that there's that passive solar gain, which is so very advantageous. In Greek times, this was done primarily for heating and conserving wood. There's a great example of this with Southern Alberta Institute of Technology's green building office on SAIT's campus, where they show by doing these things, like the Manitoba Hydro experience, they virtually use no natural gas or electricity for heating or cooling. Just some great techniques. Interestingly, this is often called passive house standards, which are used heavily along with LEED and BREEAM in Europe. And I just always find it fascinating that Canadians actually very much led this approach in developing this approach. So adding to these sort of older technologies, of course, solar panels and more glass or glazing or clear membrane if they had it. So they're really maximizing this gain. And then they're doing things like having lots of water in the equation. So you end up with water storing up that energy. And because it has the 800 times the density of air, what ends up happening is, the sun only shines 6 hours a day in the winter, say, in most of the more southern climes of Canada. But when we store up that energy in these kinds of energy storage approaches, and there's lots of those options available, then the sun from the day will allow you to heat into the night, right? And geothermal can assist, or other technologies. So this is what they listed back in the day in the 1970s. This was a demonstration facility in Prince Edward Island called ARC. And that was one of the motivations for us choosing the name of our company. And yes, they used solar panels and high efficiency kitchen appliances and a small wind turbine for electricity and composting toilets. And they saw the advantage of incorporating actually food production into the mix. So in some ways, it's really great to know that we're not on skinny branches of R&D when we're going down these paths to do these things, that there's just tremendous volume of best practice and knowledge of how to do it well. And for a lot of our mutual green building goals, it creates a whole bunch of opportunities, which we'll get into. So some will still look at that and go, geez, it's hard to believe, a R1 greenhouse with glass or our clear membrane is going to outperform from an energy standpoint. And so many will struggle with that. It's been studied for a very long time. In this case, it's a graphic from, and I'll apologize, I always butcher the university's name, but it's one of the top two universities in the Netherlands, and they've studied this from a greenhouse perspective. So what they looked at is, a lot of people would think, well, if I build a plant factory, as they call it here, and I have, say, R30 insulation, which was this test case, how much more efficient would that be as opposed to an R1 greenhouse? And the fact is that's the numbers. What we end up seeing is that in Sweden or the Netherlands, the greenhouse will use half as much energy. And interestingly enough, what happens with that insulation, that R30 insulation, is that rather than needing heating, as you see in these two examples, you actually end up starting to use an awful lot of cooling for comfort of plants. And so being aware of how efficient this is, and then layering technologies for these designs, we can really cater to very, very low energy requirements. When it comes to cooling, that reverses. So this example in the UAE, it's all about cooling, and cooling greenhouses drive the energy costs way over an insulated building. So, of course, location specific, but none of Canada has the conditions of UAE, as you all know. So what kinds of applications? Well, this is an example of a retrofit at Harvard University, where they needed more space, wanted more space. It's a very historic building. So they designed it so that nowhere from the ground can you see this addition. The structure was, as so many, designed for 100 pounds per square foot of a weight structurally. And so this building could be put on top because it is about 3 pounds per square foot. And so they created their space, quite energy efficient space, meeting all the architectural controls. In this instance, in downtown Calgary, literally right over a TD bank branch, what was the case is that they wanted more space, but they wanted to extend the season of their patio. They had a leased patio on the rooftop here, and it always did very well, but 100 frost-free days, not all that many days of use. So Brett Wilson saw our greenhouse at Sprung's campus and said, gee, it would be great to have this on our Kaylee's restaurant, which is now called this area is called the patio. But anyway, it was intended initially to extend the season. But what they found is just like Manitoba Hydro in that earlier picture, you saw people in the utility savings corridor. People always like natural light. It's why we always, have a certain competition for the windows on the exterior and less competition for the uh, offices on the interior. Same thing here is because of all the natural light and so forth. It became a very, very popular space, such that they ended up installing some heating equipment. These panels are not, as you can see, they're kind of white. They let in about 22% of the sun energy. So they needed some supplementary heating, but they now operate this space year round. And an example of many examples of where you can find revenues, it dramatically extended the amount of space being leased in the building year round. So the building owner enjoyed that. Kaylee's restaurant ended up with this space becoming one of the highest dollars per square foot restaurant areas in the city for the last, I think, 3 years. So very successful. For the municipalities in the audience, we'll give the swimming pool example. Because this is just a sprung building that's not taking advantage of much in the way of solar gain. It's a R30 building, but it could be clear panels, as you see with this, and so we could even do better. But in this example in Idaho, and that's a picture of the interior of the building, what we're showing is that the building is using all in heating, dehumidification, pumps, lights, all electricity use. They're using 370 kilowatts per square meter per year. And the Energy Star benchmark for swimming pools is 990, and then these are various averages in other countries or the British best practice. So what you see is an extremely low energy use, thanks to the sprung structure. And if we were buying that kilowatt usage at 8 cents a kilowatt, if everything was electrical, the cost would be almost 260,000, and you can see the dramatic savings and why the payback is fast and strong. In the Netherlands, in terms of growing revenues, they don't have land. They're land impoverished in a way. So what they did many years ago is leveraging glass greenhouses and polycarbonate greenhouses, etc., is they put that energy efficiency into effect, primarily with tomatoes, cucumbers, and peppers. And the fact is, despite the US having 237 times more agriculture land than the Netherlands, the Netherlands has become the second largest food exporter. Well, what we see at ARC is, with a lot of buildings, you could see it in the Manitoba Hydro building, you could be growing various types of food. You can see it in all kinds of examples. And in extreme cold, this is a study that Manitoba Hydro did with their Energy Smart program. And so what they're looking at is our passive solar techniques, passive house techniques, which in the greenhouse world somehow started to be called Chinese greenhouses. And this is the modeling they got. And what you see is on that particular day, not all that cold, and then they were able to achieve 30 degrees C temperatures. But what you see in this Eli, Manitoba greenhouse example, that's a picture of the building, is that even though at night it got to minus 30, and so this wouldn't be ideal conditions for plants, so you would want to have some type of supplementary heating, lots of options there, not just natural gas. But the fact is even at minus 20, the passive solar gain in here at 3 o'clock in the afternoon and a couple of hours around that, they're actually using no supplementary heating, just the sun doing its work. They hit ideal temperatures for plants or something over 20 degree C, or most plants anyway. So with our green membrane or clear membrane, what we end up with for greenhouses, but we're also using it for various commercial buildings. We just did a soccer facility in New Zealand, with part of it being the clear membrane. And the reason it's so advantageous is because it lets in so much more sun energy. So that's various types of the membrane. And this is glass, right? Which is usually considered, gee, that's the most translucent you can get, isn't it? And it has been. But this clear membrane was developed for various purposes, including greenhouses, and has been used in greenhouses extensively in Japan and other locations in the world since the late 1970s. So very, very well proven. And arc with sprung has made it into a tension membrane material for the first time. So it gives us that 2% air exchange. But why does glass not let in as much sun energy? Well, glass is made from sand. Sand always has iron in it. It's very expensive to remove. It's one of the reasons why solar panels are so expensive, because we remove the iron to get more passive solar gain from the sun. But with the clear membrane, we don't need to remove the iron. And so we end up with gaining something over 20% more solar energy than if you build with glass. But I mentioned to you other techniques of how you can use that and turn those precious hours of sunlight into heating all day long, and actually over the seasons. So this is our actual tension membrane panels in our demonstration greenhouse at Sprung. You can see how translucent it is. But under glass, we would lose or not have 20% of the energy that we use in these concentrated solar panels. So solar PV operates at about a 20 to 24% efficiency level. Solar thermal or hot water panels operate at something around a 40% efficiency. These concentrated solar panels operate at 70% efficiency or slightly above. And people sometimes wonder if it works, but we've all experienced it because we've all played with magnifying glasses. And so on the coldest day of the year, if I hold the magnifying glass steady enough, long enough, I will light this paper on fire, won't I? And so what we're doing here is this is facing in just to show you the panel, but it would normally be facing out, obviously. And it directs all the sunlight to a black pipe. And so for our greenhouse, this is our lead boiler in the building. And it could be for any building. It can be a swimming pool. It can be any retrofit, whatever. But now we're not using natural gas at all. We're creating 80 degrees C hot water in this instance. You can actually create steam if you want. And therefore, if you have the right volumes, you can store it literally over and use it overnight. But as greenhouses have been doing for a very long time, they will store hot water that they generated in the summer so that they can use it in December and January. And so that's where these technologies end up taking you to. We have quite a few examples of various applications of greenhouses for growing, plant factories, in this case for growing fodder for livestock. In this case, it's housing growing tilapia. This was an example of growing shrimp. And so lots of examples. This was tilapia in Hawaii. This was Utah. A bunch of these are in the Caribbean and other places. I will stop there and look forward to any further questions that you have.